In case you can't remember, igneous rocks are the rocks that are formed from molten lava or molten magma, depending on where it cooled. Remember, magma is the molten rock that's found underneath the Earth's crust, and lava is the molten rock that's escaped the Earth's crust and it's got out into the atmosphere. So both of those solidify and make igneous rocks. When you look at them, you can actually divide them into two groups. Ones that have big crystals that you can see easily with your eye, and ones that have tiny, tiny crystals that you can't actually see with your eye at all. So granite and basalt are very good examples of them. Granite here, you've got your big crystals here that you can easily see, and that crystal there, all that same color there, means it's made out of the same type of mineral salt. They tend to group together with salts that are the same as them. So that's all one type of salt that's formed a big crystal in granite. And over here you've got tiny, tiny crystals in this basalt, and again made out of mineral salts, but tiny crystals have been formed. So the question is why? When you have a look at these granites and ones like it with the big crystals, you tend to find them deep underground. Basalt and a lot of the other igneous rocks with tiny crystals to no crystals that you can see, you find them on top of the ground, on top of volcanoes, under the ocean. So the question is where they solidify and cool down got to do with the type of crystal that's found inside them. So the ones that are deep underground, it's going to take them ages, maybe years, before they finally cool down and turn into rock, whereas the ones like basalt that have been literally blown out of a volcano, they end up solidifying and cooling down really quickly, and therefore have not had an awful lot of time to form. So you're going to conduct an investigation to see if how quickly they cool down does affect the size of crystal that they grow. So we are going to be putting together two lots of, well, not quite molten rock because it's very hard. There's very high temperatures to actually melt salt. So instead of melting it, we're dissolving it. But still, you're going to actually allow it to cool down and solidify either quickly or slowly. So in your experiment today, you're going to have a little measuring cylinder. So graduated cylinder like this, and it should be about 10 ml in size. And you're going to add to it the dissolved salt that you have, sodium chloride. It's in a little container that looks like this with a squeeze top on it. You're going to be putting into there 6 milliliters of dissolved salt solution. You're going to measure it, and you're going to put 6 ml into 2 petri dishes. So today you're going to be setting up this experiment. First of all, you're going to be given 2 petri dishes per group, and you're going to be asked to label them fast cooling and slow cooling. So the mineral we're going to be using is sodium chloride, and its chemical formula is NaCl. You may also use alum, but we may or may not be able to put that out today depending on where we are. So you're going to have dissolved sodium chloride. You need to label with the pens the edge of your petri dish, just like I've shown here. And then you're going to add in your dissolved mineral salt. So your saturated solution of sodium chloride will come in little bottles like this. You need to measure 6 ml, right there, 6 milliliters of solution into your measuring cylinder here to get it exact. And then you're going to be putting in 6 milliliters each into each of these petri dishes. 6 ml into each one. Once you've done that, you're going to be putting them in carry cases for slow cooling and fast cooling, and we'll be taking them back into the lab to get them to start cooling down. So that's essentially the way you set up your igneous rock experiment.